Hi, how's it going? My name is Carl Diaz, and today we're going to be looking at a couple problems looking at work and how to use work to solve for velocity and to solve for force. So let's kind of get going here. All right, so our first situation, again, we don't want to have it all drawn out here, but we could. I guess that's a weird thing to see there. Right, there's this person and they're pulling on this box this way. Okay, I didn't have it there, but I guess we have a little of what's going on, right? So we know the tension's 50 newtons, we know the mass of the box, we know it started at rest, and we know the mu, okay? And the question was saying how fast is it going? Oh, and we know the displacement. I erased it when I was trying to get all this up there. I realized, and now it's not there. Change in x is 10 meters. All right. So we know the tension, right? We know the mu, we know the mass, and we want to know the final velocity after those 10 meters. How fast is it going? If it started at rest, it initially started at rest. Okay, so first you want to draw your free body diagram. Now I know this is work, and I know you see Newton laws up here, but they're important. We still need them. We just might not be using acceleration directly, right? So you want to draw your free body diagram. Again, tension's that way, right? We know that's a rope. That's the block is being pulled by a rope. There's tension, right? There's friction opposite, normal force in mg, right? We know we're pretty comfortable doing that now, I'm sure. And we want to write Newton laws for each side, so we know that we started at rest and we're going to be at some speed. So we know there's acceleration in this direction, so we know Newton's first law or second law applies. Then we just want to fill in the equation from our free body diagram. So tension's positive, friction's negative. Then we were given mu instead of friction, so we know we got to turn, right? We know friction's equal to mu times the normal force, so we got to turn friction into that, right, to make our equation correct. But then we also know that when we do in the y, right, that normal force minus mg, right, it's their balance, so it's Newton's first law for the y, and then it's normal force minus mg. When we solve that, we see normal force is equal to mg. So when we pop this in here, we're kind of doing two steps. We're replacing friction with mu times the normal force, and I'm also placing normal force with mg to give us this equation, just kind of taking a step. You should be able to make some jumps like that now. Okay, that should be fully comfortable to you. So that's a good equation for our, oops, I squared that off, for our x, but there's some important here because when we're here in work, we're not necessarily, you don't hear us talk about this so much, but we're still super concerned with what here? We know work, net work of a system, right? Which means the kinetic energy, the change in kinetic energy, the change of potential energy, right? These things, right? They are important to work. So even though we're writing this equation for Newton's second law, this side of it isn't so important this time. What's important is on this side, because this is the net force. And we know net force, if you watch the concept video, so go watch the concept video, we know that net force gives us net work. And we can use the net work, right, to solve for changes in kinetic energy where we see velocities in there, right? So that's how we want to kind of think. Even though we're using Newton's second law, we're not saying anything and solving for acceleration or anything, but we're looking at, we need the net force. There's the net force, right? We know the net force is equal to ma, and we need that for our work equation, right? We know work is equal to net force times displacement times cosine theta. We know that if displacement, right, and net force are in the same direction, we know they are because we're speeding up in that direction, right? That cosine theta becomes 0 because cosine times 1 is 0, right? So it's going to drop off here when we write it. It's going to disappear, just keep that in mind, but that is what net work is equal to. We also know that net work is equal to the change in kinetic energy, right? Where the change in kinetic energy is equal to final minus initial, where each one of those kinetic energies are 1/2 mv squared, right? So we want to kind of put all these pieces together right here, all right? So we know that work's equal to F net times displacement cosine theta, right? We also know it's equal to the change in kinetic energy. So once we have that equation, then we want to drop off cosine theta, because that turns into, sorry, not 0, I wrote 0, it turns into 1. Cosine 0 is 1. I said that backwards earlier, I apologize about that. But cosine, you should know this by now, because you've been doing this quite a bit, right? So cosine 0 is 1. And then, since that drops off, we're left with F net times displacement, and then we expand it out, change in kinetic energy to 1/2 mv squared final minus 1/2 mv squared initial. And we know that the initial velocity is 0, right? That's what this is trying to tell you. So this is going to drop off, leaving us with, when we fill in a final equation, now I guess we're making some steps here, but you should be able to do it here with this F net, right? We have F net times displacement equal to 1/2 mv squared final, because this 1/2 mv initial is 0, right? That's the equation where F net is what? Right here. That was the point of getting this. This is F net. Tension minus mg times mu, not ma, this side. So that needs to take the place of F net, which is what I did. Tension minus mg times mu, right? It still stays multiplied by displacement, then equal to 1/2 mv squared. And then from this point, it's just as easy as solving for velocity here, right? Where 2 is going to come over, m is going to come down, so 2's up here, multiplied by, right here's the displacement, right here's the net force, right? This 2 just came from this 1/2 coming over, and this mass just came from this coming down, right? So we're left with the v squared here, and then once we do the square root of all that, right, which is right here, that's going to be the final velocity after 10 meters. You punch 10 meters in there, put all those, you have all those numbers to put in there, and you'll get it, okay? Now, let's see what happens when we're at an angle. Do things change? Are things weird? Right? Well, first of all, right, I kind of saved us some time by drawing the free body diagram by breaking mg up into its components, where we know a component of mg when we're on a ramp points down the ramp, and a component mg is balancing the normal force on the ramp, right? So we know this from all that Newton law stuff we did, right? So we can again write an equation. Now, over here, I wrote sum of forces are equal to y so that I can fill it in here, right? But as you notice over here, there's no sum of forces equal to y, and why is that? Because we don't need the y, in terms of the y, normal force in mg, they're 90 degrees to displacement, right? So when we put it in here, if we were to look at the work from normal force, right, it'd be the normal force times displacement cosine theta, right? Well, displacement's down the ramp, which would be 10 meters in this case, but cosine theta, right? The theta is 90 degrees. There's normal force makes a 90-degree angle with displacement, right? So cosine 90 is 0. This cosine 90 is 0. That makes this whole term 0. And 0 times all this is 0. So there's no work done by normal force or mg. We know this, so we don't even have to look at it. All right? And in this question, I think I forgot to mention, we're looking for friction now. We want to find force. How do we use this idea to find force? Because it's a tool to also find force, okay? So first of all, we're not even concerned, so back to what I was saying, we're not concerned with the work in the y, because cosine theta for this one and this one is going to be cosine 90, where it makes that whole term, cosine theta turns into 0, and when 0 is multiplied by anything, it turns into 0, right? So that's what we know. So we're not concerned with the y, just the x. So I do my sum of forces in the x. Also, we know that's where the net force is, because it's speeding up down the ramp. We know it started at 0, and now it's at some speed at the bottom of the ramp, right? So we want to do our free body diagram, right, and say mg's positive, or fill in our equation from our free body diagram. So mg sine theta is positive, pointing down the ramp. Friction's up. Now, we're looking for friction, so we don't need mu or anything like this, okay? We're looking for the actual value of friction, so we're not changing anything, right? And again, this equation's important for one reason. Yeah, it's equal to ma, but this is the net force over here, right? The net force is over here, and we know the net force goes into our net work equation, right? These are our tools, again, that we need to put together to answer this, right? Where we know net work is equal to this, net work's also equal to change in kinetic energy, and what change in kinetic energy is equal to. So when we start to put those together, right, now I took some jumps because I kind of explained the steps over here, right? I know I'm going to be using this equation for this. Displacement and net force. We know net force is down the ramp because we're speeding up down the ramp, are in the same direction, just like over here. And we know that when they're in the same direction, cosine theta is 1, positive 1, so it just drops off. So I didn't write it here. And then all that's left is the displacement and the net force, right? And the net force is mg sine theta minus friction. And then we know that the net work is also equal to the change in kinetic energy, which is 1/2 mv squared minus 1/2 mv squared initial, right? We know this is 0 right here because we started at rest, right? That velocity becomes 0, which means this whole term becomes 0. So when we rewrite it, we're left with this. Now what I did is I multiplied displacement in because I need to get friction by itself. In order to do that, I have to multiply displacement in. I have to disperse it, right? So I have displacement times mg sine theta here and displacement times friction here. All right? Equals to 1/2 mv squared final because this dropped off. Now remember, we're trying to find friction here. So now it's just some algebra, right? Where I'm going to add this over. So what I did, because I wanted to keep friction positive, is I added friction over and subtracted 1/2 mv squared over here. So I wanted friction to become positive. So I added it over, right? Because I'm not concerned, I just want to find the value of it. So I added it over, all right? And brought it over to this side of the there's the equal sign, right? And then I brought 1/2 mv squared final over on this side. So there's 1/2 mv squared subtracted from mg sine theta displacement, and there's friction times displacement on the other side of the equal sign. And now it's just as easy as solving for friction, which is dividing by displacement, and there we go, there's friction. That's how we solve for force. So again, this is using work, right? We use some different concepts. If you didn't know the concepts, go watch the concept video for this, okay? Because it's super important. But we use work to find speed, how fast something's going, right? And we also use work to find force, right? So it's important. Like before this, we were using kinematics and Newton laws to get this stuff, to find force and to find speed, right? Well, this is how we do it when acceleration's constant or not. We can use changes in work, changes in network, changes in kinetic energy when acceleration's constant or not. And if you're confused about that, go watch the concept video to solve these things. So I hope this was helpful. Make sure to keep watching these videos, and I hope they're really, really helpful, and I'm super, super proud of you for making it this far. You kind of made it halfway through, so keep pushing through. I know you can do it. I know you can. Don't let this class slow you down. You're going to reach your goal, and not only are you going to reach your goal, but you're going to do it well. You're going to go out there, and you're going to change the world. I know every single one of you are. Don't worry about this class. We will get you through this class. Watch these videos. I'll get you through the class. Reach your goal for me, okay? Go out there and be the best you can be. Change this world, make it better. All right? That's what we got to do. That's our job, is to make it better. I'll see you on the next video.